Welcome everyone to my talk. This is Yuan from Acuity. So today we are going to talk about cloud-native distributed machine learning pipelines at scale. First of all, a little bit introduction about myself. I'm a founding engineer at Acuity.io. We are the enterprise company for the Argo project under CNCF. I've been very actively contributing and maintaining projects in the open source community. For ML frameworks, I've been maintaining projects like XGBoost, TensorFlow, Metric Learn, that's currently in scikit-learn contrib. Also, from infrastructure side, I've been maintaining projects like Argo Workflows and Kubeflow. And there are a couple of books that I authored. The first book, Distributed Machine Learning Patterns, is currently still in draft, but it's available on many MIP, which means that you can read it for free online in your browser. And feel free to contact me. I'm on Twitter and LinkedIn. You can contact me via that handle. Feel free to schedule a chat with me if necessary. So today's agenda, first of all, we will be talking about the components of distributed machine learning pipelines. And then we'll talk about Python scientific ecosystem and the existing workflow orchestration tools in Python. And then we'll talk about cloud native and Kubernetes, explain what those are. And after that, we'll talk about Kubernetes native machine learning pipelines. And last but not least, we'll talk about how we can stay stronger together and the future outlook by combining those ecosystems together. So what are the components of distributed machine learning pipelines? The first part is the data ingestion and data pre-processing. You may encounter things like batching and caching, streaming if you are working on a streaming-based data set. And you may perform some feature engineering and perhaps require some feature stores in order to make the model training and model serving more consistent and make your features that's engineered to be better served in production. The second part is the distributed model training, and which would involve maybe hyperparameter tuning and model selection or neural architecture search for deep learning models. And in order to run distributed model training in a distributed environment, you have to select particular training strategies. So for example, parameter server-based training strategies and all reduce or collected communication strategies. And there's also all sorts of optimizations you can do via scheduling techniques. For example, priority and Gantt scheduling, elastic scheduling if you are running your distributed model training workloads on preempted spot instances. And next is the model serving component. You may want to replicate your model serving services. If you have a large number of model serving requests, you can shard your services into different shards to handle very large model serving requests. And there's also event-driven processing as well. And last but not least, there's workflow orchestration that's required to chain all the steps together into a complete end-to-end distributed machine learning pipelines. Also check out the distributed machine learning patterns book that I mentioned. It includes many of the patterns we will talk about in this presentation as well. Let's take a look at the Python scientific ecosystem. At the very bottom and its core is the Python language. And on top of that, there are core libraries like NumPy, Matplotlib, SciPy, Pandas to help with numerical computations, scientific computations, data frame, data manipulations, and so on. And then on top of that, there are specialized libraries such as scikit-learn for machine learning, stats models for performing statistics in Python, and Dask for parallel computation and orchestration. And at the very top, there are domain-specific Python libraries. For example, AstroPy for astronomy, PyMC3 for probabilistic statistics. And then there are a lot of tools that are written natively in Python. Here, the Python native means that everything's implemented in Python without any other languages and so on. So here, there are 3 popular workflow orchestration tools in the community that you can choose from in order to chain all the steps together in your machine learning pipeline. So what is cloud native and Kubernetes, or K8S? You also say it in Kubernetes. So I came across this container coloring book for kids during KubeCon North America a couple of weeks ago. And this is a great book for kids for coloring, but also a great book for others to explain and understand various concepts around cloud native and Kubernetes. So imagine once upon a time, there were 3 little pigs. They each needed a place to live. And obviously there are a lot of options for them. You can choose a house or duplex or an apartment, or even living in the park. So consider, imagine a little piggy is an application. An application need to choose a place to run, right? So application may choose a house, which is the most secure, because if if this particular house is ever broken into, the rest of the houses, the other apartments, houses are still safe. But if each of the little piggy lives in a separate house, that means more maintenance for all the houses. So think of piggies as applications. They live in containers, different isolated environments. And once you move to an apartment, you need to buy different furnitures and appliances that meet your daily requirements in order to achieve high living standard, maybe. So in other words, the resources needs to be managed inside the containers. So Kubernetes, that's where Kubernetes comes into play. Kubernetes automates the deployment, scaling, and management of containerized applications. So make lives easier for those little piggies. What does a Kubernetes native machine learning workflow look like? First, let's talk about the Argo project. The Argo project consists of a set of Kubernetes native tools for deploying and running applications, managing clusters, and do GitOps right. GitOps, in a sense that we are storing everything in Git, we are versioning everything, making sure Git contains the source of truth to reflect your infrastructure. So there are 4 core projects under Argo. The first project is the Argo Workflows. It's the Kubernetes native workflow engine. And then Argo Events is the event-based dependency management for Kubernetes. There's also Argo CD, which is for declarative continuous delivery with a fully loaded UI that's needed for almost every developers in this area, so that they can just take a look at the UI to see what's happening in their clusters and so on. And last but not least, this Argo rollouts project that provides advanced Kubernetes progressive deployment strategies. And the Argo project is used and trusted by more than 100 80 end user companies, 3,000 Slack members, 1,000 contributors to the code base, more than 20K GitHub stars. And the project, this is a diagram from CNCF that provides a project rankings for developer velocity based on project activity, such as the activities on pull requests and issues, number of commits, and so on. And Argo is one of the fastest growing and developing projects in the CNCF Foundation. Argo Workflows. So let's first talk about Argo Workflows. It's a container native workflow engine for Kubernetes. The main use cases for Argo Workflows are machine learning pipelines, data processing, ETL, infrastructure automation, continuous delivery, and integration. Here's a screenshot of what the Argo Workflows UI looks like. Argo Workflows contains a set of CRDs and controllers that are Kubernetes native. So CRDs are Kubernetes custom resources, for example, that natively integrates with other Kubernetes resources, such as volume and secrets, and so on. And Argo Workflows provides interfaces such as CLI, server, UI, as well as Python and Java SDKs. The CLI is used to manage workflows and perform operations, such as submitting, suspending, deleting workflows through command line. And the server is used for integrating with other services, REST or gRPC interfaces. And the UI is used to manage and visualize workflows and the artifacts created for the workflows, the logs and resource usage analytics, and so on. Here's a basic hello world example of Argo workflow. So we basically specify the container image and the command to run for this workflow. And this example on the left-hand side is a custom resource created. So we specify a custom resource for Argo Workflows to submit to the Kubernetes cluster. So you can submit any Kubernetes native resources to Kubernetes cluster. On the right-hand side, that's perhaps the most useful to the Python community. You can specify a Python script providing the source code. For example, here we are generating some random numbers using the Python rthing image. You can also specify this as a container if you like, such as in the hello world example. You can just specify the exact Python code command to run instead. Here's an example of a DAG created by Argo Workflows. So a DAG is a directed acyclic graph that consists of steps. So for example, here, this DAG consists of A, B, C, D steps, and each of them has their own dependencies. For example, step C depends on step A, and step D depends on B and C. And this is a visualization provided by the Argo Workflows UI. And here's a simple coin flip example to showcase the conditional syntax. So here we can specify the condition to say whether we want to run the next step or not. So for example, here we run flip coin step first, which is the Python script we just saw. And if the result returns heads. Then we run the template called heads, which also prints another log saying it was heads. Otherwise, we print it was tails. So we specify these conditionals inside the when clause in the different steps. Well, that's a lot of YAML files and YAML files everywhere. Can we do everything in Python? Of course. We want to keep calm and code in Python, right? So we got a lot of options. So the first option is Kubeflow pipelines. So Kubeflow pipelines is a sub-project under the Kubeflow project. It's purposely designed for machine learning pipelines using Kubeflow. And the second project is Kuli. Kuli is a unified interface for constructing and managing workflows in different backends, for example, Argo Workflows. And Argo Workflows also maintains its official Python SDK, but rather low level, but you can interact with other features that's provided by Argo Workflows. So a quick example using Kuli, if you want to build a Kuli coin flip workflow in Python, this is how it looks like. That's very different from the YAML that we see. So here we define a Python function, and we define the flip coin function step that runs that particular Python function. And here are the heads and tails step. Both of them are defined in terms of Kuli run container. And we can call flip coin step and check whether its result is equal to heads or tails, and call the corresponding steps for heads and tails conditionally. And here is how it looks like for a DAG defined in Kuli Python SDK. So you define a generic Python function called job that runs a container. You can specify the name of the job. So this can be reused for multiple steps. So here, for example, we are building a very simple DAG that has a linear relationship. For example, B depends on B depends on A, and D depends on B, and C depends on A, and the DAG example as well. So here we can use Kuli.DAG to specify the dependencies altogether to build a diamond-shaped workflow. Next, I want to talk about Argo Events. It's the event-driven workflow automation framework. Currently, it supports events from more than 20 event sources, such as webhooks, S3, GCP PubSub, Git, Slack, etc. And it supports more than 10 triggers. So based on if anything new if we receive any new events from those event sources, we can trigger things like Kubernetes native objects. We can trigger an Argo workflow. We can trigger AWS Lambda, Kafka, Slack messages, and so on. So we can use Argo events to manage everything from simple, linear, real-time to complex multi-source events. And Argo events is also cloud events compliant, so that you can use this standard common specification to integrate with other systems very easily. So what would a typical workflow look like with Argo workflows and events? So here, let's assume we are watching events from GitHub. So for example, events like commits, pull requests, tags, and so on. So Argo events is responsible to watch and receive those events. Once it receives events, it will trigger machine learning pipeline with Argo Workflow. So in other words, the Argo events triggers a pipeline that's defined and chained together by Argo workflows. So a simple workflow may look like this. The data ingestion, that's responsible to ingest data from the data source. You may have a cache store that's in place using Argo or Kubernetes to check whether the data has been updated or not recently. In order to skip this particular data ingestion step, if nothing changes in the data set. Otherwise, you have to execute that data ingestion from scratch, which with a lot of resources. And after that, after we've ingested the data, we start model training, right? So model training we can have multiple workers and multiple data sets so here, for example, we are running the distributed model training using OreReduce. We will zoom into that soon. So the model training may consist of code written in TensorFlow, PyTorch, and so on. And then you can use Kubeflow to submit a distributed TensorFlow training jobs so that algorithm developers don't have to worry about the infrastructure side of things. And Kubeflow will communicate with Kubernetes to request enough resources for each of the workers, parameter servers, and so on. And then TensorFlow can just focus on the algorithms, the models, and so on. There's also a project, a sub-project called KTIP in Kubeflow that's used for hyperparameter tuning and neural architecture search, early stopping, and so on, written natively in Kubernetes. So you can use all the tools available to build a really cloud-native, Kubernetes native, container native machine learning pipeline in your distributed Kubernetes cluster. A little bit more details on the distributed model training side. So you can have multiple workers. Each of the workers consume a particular data partition from the data partitions that you partition ahead of time from the data source. So this diagram is taken from my distributed machine learning patterns book. If you're interested, please take a look. You can read it free online. Last but not least, I want to mention that we should stay stronger together by combining what's the best of all the ecosystems. So in the future, as data scientists, our developers, we can focus on developing tools that are most valuable for scientists. For example, specialized algorithms, specialized numerical computation algorithms, and so on, such as scikit-learn or TensorFlow. We can embrace the Kubernetes ecosystem. So there are many ways to do that. There are Kubernetes native operators and custom resources, for example, provided by, for example, Kubeflow provides custom resources and operators on Kubernetes so that you can run TensorFlow jobs, PyTorch jobs in a distributed fashion very easily on Kubernetes. And Argo Workflows provides custom resources and controllers to help orchestrate your jobs to achieve the maximum benefits brought by Kubernetes. And there are projects that integrate well with Kubernetes. For example, Dask, Ray, and Spark, they all have their own operators that could help those frameworks to run on Kubernetes as well. In other words, in the future, the architecture will be more decoupled into different areas, focuses. For example, for an infrastructure side, the architecture could focus on ML ops, DevOps, or data ops. That's focusing on data set and feature stores, those kind of things. And there are frameworks, architectures. So for example, machine learning framework, deep learning frameworks, or data visualization frameworks, scientific computing frameworks, they are focusing on the framework itself instead of focusing from the infrastructure, worrying about different cloud provider, different cloud vendors, the domain-specific experience, and so on. And here are some screenshots for the first one. On the top is the LFAI and data landscape that contains a lot of AI and data related projects. And at the bottom, this is the CNCF Cloud Native Interactive Landscape. So this landscape contains a lot of projects that are in the cloud native scope. So I think most of them are cloud native and Kubernetes native as well. And they tend to play well with each other. So by combining the best from both of these communities, for example, AI community, data community, cloud native communities, PyData communities, we can focus on what's the best, what brings the best benefits to our scientists. That's it for the presentation, and feel free to contact me via email. I have the same handle on almost all the social media. And feel free to schedule a chat if necessary to talk about open source and any potential collaboration. And you're welcome to join the Argo community and the Kubeflow community to talk about how to contribute and how to get involved, or send us bug reports, feature enhancements, and so on. Thank you for listening.